Okay, welcome everyone to the talk of Claudia Meza-Cuadra, if I pronounce it right, on the topic of video games and gender gap in computer science from the Network Inequality series. First, I would like to introduce Claudia. She's an applied economist working in the fields of gender and labor. Her research focuses on investigating drivers of gender inequality in the labor market and shocks to gender norms. She's currently a PhD candidate and researcher at University Pompeu Fabra in Barcelona, and she previously worked in the research department of the World Bank and the US Environmental Protection Agency. So, thank you for accepting the invitation for the talk, Claudia, and you have about 1 hour to share your work with us.
Great. Thank you for the introduction and the opportunity to present my research. So I'll just start right away. As you said, my research is exploring the relationship between video games and the gender gap in computer science. And the motivation for my work is that although there's been a lot of growth in the share of women studying science field degrees over time, there's a lot of variation within the fields of science. So this graph shows you the share. I guess you can't really see the bottom one too much, but this is showing you the share of women obtaining bachelor's degrees in the United States over time. The purple line shows that there has been an increase, for example, in the percent of people studying physics who are female, and likewise with engineering, and that's the case for several other STEM fields. So you can see that while it was really these fields were really dominated by men in the 1970s, this has really changed, and in physics is almost 50% now of the people getting bachelor's degrees in the United States in physics are women. But that's not the case with all the fields, and in particular computer science, which is the focus of my research here. It seemed to be following a very different path where there were more and more women studying computer science in the early years. So you can see that the trend is sharply upwards up until around the mid-1980s. However, despite almost 40% of computer science students being women by 1985, this has decreased pretty sharply in the period between 1985 and 2000, and it's never fully recovered. So now computer science is actually the most male-dominated of all the science subfields in the US in bachelor's degrees. And there's been this sort of raises a puzzle, and there's been some research trying to identify the drivers. In particular, there's been qualitative research that showed, for instance, in the United States, that in this time period, there was a gender gap in the level of experience with computers that men and women arrived with by the time they got to university. This is focusing on particularly Carnegie Mellon University, where researchers tried to find out why women were dropping out of computer science and why they felt less comfortable if they ever did degrees. And so this raised the question, what is behind this fact? So is it that maybe nature plays a role in this, and so boys are just more interested in using computers, or potentially have a higher ability than girls, and this is what makes them more comfortable or more exposed to them? But I'm interested in exploring the second potential driver, which is nurture, that boys and girls might have different upbringings and experiences with computer as children in this time period, and that this could be explaining why young men were much more comfortable with computers by the time they got to college. And so, for instance, it could be driven by different access to computers as children, or also potentially the norms around computing that were present in this time period. So maybe parents were encouraging boys and girls differently, or there was a culture around computing which made it more likely or easier for boys to get involved. And so my hypothesis in this research is that video games could have played an important role. So specifically, in the same time period, in the early 1980s, the use of computers for gaming in the home grew really quickly. And these video games that were released early on, and arguably even more recently, were often targeted to boys. The use of video games was much more common among boys. So there's evidence about the advertising of video games, but also the content of video games. So a lot of the video games contain gender stereotypes. A lot of the early topics were based in war games or other male-coded video games. And also there's evidence that there was a lot of harassment of female users who wanted to use video games. And so my research question was whether the spread of video games and gender norms around gaming played a role in the growth of the gender gap in computer science. And so this is a brief overview of the paper where my aim, as I said, was to study the effect of video games on this gender gap in both computer science education and in employment, focusing on the United States. And the method that I used is that I used very large scale US survey data. And I used a two-way fixed effects methodology, which basically exploits differences in the early spread of video games by the year and location, state level location that people were born in. And I also tried to address some issues around endogeneity, so meaning other underlying differences which could be driving these differences in video game exposure using an instrument for the spread of video games. And my findings were that I find that, as a sneak preview, that video game exposure is significantly associated with this increase in the gender gap in computer science, and that men who are more exposed to games as teenagers are relatively more likely to attain bachelor's degrees in computer science, to work in a related field as an adult. However, they're also less likely to obtain a bachelor's degree at all, and I'll explain more of what happens if they don't obtain a bachelor's degree, and specifically whether they get other degrees. And the main contribution of the paper is that it's the career choice of men and women and the differences among them has been a source of a lot of investigation, because this has been found to be one of the still very important drivers of differences in wages. And so in my paper, I look at the role of non-academic activities and show that these activities and differences in the behavior of boys and girls could have differences, could have effects in the long term that we should consider. Also, I'm studying the gender gap in STEM, which has also been a source of a lot of research due to its persistence and the difficulty that colleges have had in changing this pattern and getting more women to study STEM. And I provide additional evidence of a driver of these gaps, which has never been identified before. And specifically, I'm contributing to the research on video games and gender, some of which I mentioned before, related to differences in gender stereotypes, harassment, and also the labor market effects potentially of video game availability. And my paper is the first to find an effect of video game exposure on career choice and college completion. Okay, so diving in, the context, just to convince you of the importance of this paper, is that young men spend more time playing video games. They have done so from the very beginning of the data that we have. Here, I'm showing you a different source of data. This is the American Time Use Survey. So this is for all 15 to 24-year-olds in the US. And we can see that the average hours per day that people in this age range spend playing games is much larger for men than for women. So it's over twice as large. And it's almost 2 hours in 2021. Here I just show you that the differences in computer use are not as large and not as consistent. So it's not that women don't use computers for leisure, but specifically gaming, there seems to be a very persistent gender gap. And this, we know from qualitative evidence, has been the case from the beginning of the spread of video games. And the data that I use specifically in my paper comes is the individual education and occupation, which I obtained from the American Community Survey in the US. And this gives me a very large sample of over 9 million adults. And I can see what they studied at the bachelor's level, as well as their field of education, occupation as adults, their state of birth and the year in which they were born. And I combined several survey years to basically get the largest sample that I can. And I am looking at video game exposure for these individuals during their childhood. And I get a measure of this by using a survey that the CPS in the US ran from 1984 to 2003, where they asked people specifically about their computer and internet use. And from this data, I'm able to get, for a smaller sample of individuals, the state, age, and gender of people, respondents, and all the people in this household, so including children, and whether the household had a computer or a laptop, and whether all of these individuals used these computers to play games. And from this, I construct a measure at the state and year of birth level, which is the share of people who were your age and who were born in the same state as you, who were playing video games when they were young. And I combine these two data sources based on this birth information. Okay, and this is the variation in my treatment variable. So this is the share of people in your birth cohort and birth state who played video games when they were teenagers. And you can see that this exposure to video games really shot up on average in the early 1980s. But what I'm using is variation in this also by state. The main empirical strategy that I use for my analyses, as I said, is a two-way fixed effects regression. And I use it as an outcome whether a person was studying or working in computer science. And then my treatment here, as I described, is the share of people in your birth cohort and state who were playing video games when they were young. And what I really focus on is how this interaction, it's the highlighted term beta 3, how video games specifically affected, differentially affected boys. So because I also include a number of controls, so to capture variation in other variables at the state cohort level, such as the share of adults who had higher education, the average household income, and I use a lot of fixed effects to try to capture the unobserved variables that I can't measure directly. And I, also cluster my standard errors at the state level. But basically what this is showing you is that I'm focusing mostly on this interaction of this indicator for each individual in the ACS being male with this share of video game exposure that I calculated for the US in this time period. These are my sample statistics. Just important to see that I have a really large sample because I pool all these years of the ACS. So I have over 9 million observations. And my birth years in my survey go from 1980 to from 1967 to 1994 with an average of 1980. You can see here also that the overall share of people actually studying computer science in the US is quite small. So on average, only 1% of people study computer science bachelor's degrees in my sample. But the average video game exposure is around 30%. So around, on average, 30% of people's peers were playing video games when they were young. And I also have a lot of variation in this variable. Also, the share of people working in computer-related occupations as adults is only around 2%, so quite small. However, I would argue that due to the relationship with technological development, these gender differences could have really important spillover long-term effects. Oh, and also I forgot to point out that since I only can see people's education in the past, I focus on people who are 22 and over to make sure that they're of an age at which they would have completed their bachelor's level education. Okay, I'm not gonna go into my IB strategy in detail since I guess this is not really an economics talk, but I will briefly just give an overview. So as I said, I have a second strategy for my analysis, which uses an instrumental variable to try to address the fact that the share of people who are playing video games in your state when you were young may be endogenous. So that means that it could be correlated with other characteristics of this place and time. So they could be correlated with higher levels of technological development, educational quality, socioeconomic status, for example. And what I really want to capture is how much of the variation in probability that people go into computer science is not driven by these other factors and is just driven by video game exposure. And so I construct an instrument for video games, combining two different sources. So first, I calculate density of video game arcades in 1985 by state. So this means that I have the number of arcades in your state in one period of time. And I combine that with the video game sales when you were young. And this allows me to get time and geographic variation for my instrument. Why do I use arcades? So here you can see what an arcade looked like. And arcades, there's been evidence that they were places where young people would first be exposed to games often. So they would be very popular hangout places in after schools, and they did tend to be more male dominated from what I've seen in the survey literature, but they were obviously open to both genders and gone home and then, been more likely to ask their parents to get them computers so they could play these games more. And I get a measure of where arcades were in the US from an industry trade publication, and then I aggregate them to the state level. And yeah, just so you can see it, there is a lot of geographic variation. These are all the locations that I use to calculate my density of arcades. Just to show you also that there's kind of the expected level of variation, so in your state per area. So the number of arcades per kilometer squared can vary from 8 to 1. So yeah, this is what I use as my instrument to try to capture the part of exposure to video games, which is exogenous and not driven by these underlying factors that I mentioned before. Okay, and as I said, my instrument combines this geographic variation with time variation, which comes from a list of video game releases and data on what were their total national sales. Okay, this is a lot of detail. I'm just going to skip that for now. Okay, so I'm going to move on to the results. as I said, my main finding is that there is a positive effect of exposure to video games on the gender gap in computer science. This table shows on the left 2 columns, the two-way fixed effects regressions that I described before, and on the right, in the columns 3 and 4, the regressions using this instrumental variable that tries to address some of the endogeneity in video game exposure. And in the third column, third row, which I've highlighted here, I'm showing the coefficients on this interaction term, which I largely focus on due to its being more likely to be exogenous, and so that I can attribute some of the variation to video game exposure. So I find that 1 standard deviation increase in video game exposure leads to an increase in this gender gap in the likelihood of studying computer science at the bachelor's level of between 8 and 26%. So the estimated effect is slightly larger, or I guess significantly larger, when I use my instrumental variable, suggesting that I'm able to address some of the endogeneity and that there is a causal underlying effect. As you can see, I also showed 2 different specifications. In the first one, I don't include the controls or a state time trend. And then in the second one, I include all of the controls that I can in order to better isolate the exogenous variation. Now, my second set of main results, as I mentioned, are related to the probability that an adult that I see in this ACS survey is working in a computer-related field. I find a similar size effect, also smaller when I use the two-way fixed effects, but positive and significant, and larger once I instrument for video game exposure, and suggesting that more video game exposure not only leads people to be more likely to study computer science in college, but to also be more likely to be working in what they call a computer-related field as an adult. So yeah, just to clarify that, in the survey, people are asked specifically whether they work in a computer-related field. And this includes all sorts of, all sorts of computer-related fields. Some additional results. So I was interested to see if men are relatively more likely to be studying computer science. Is there something that they're less likely to be studying? And it turns out that yes, men more exposed to video games, using the same approach, I can show that they're less likely to be studying arts and other social sciences, as well as other STEM fields, in particular biology. These are those results. So you can see that the sign on the interaction is significant, quite consistent and negative, so suggesting a shift away from these other fields for men. Yeah, I'm showing it broken out here by physical sciences, biological sciences, and engineering sciences. And you can see then columns 3 and 4 that the coefficient on the interaction term is larger. So men are in particular shifting away from these other humanities, arts, and from biology. However, as I previewed before, I also find actually that some of the men who are, so compared to similarly exposed women, men are actually less likely to get a bachelor's degree at all. And this was surprising to me, but it's a very robust result. So I find using the same 2 approaches here, when the outcome is just whether a person obtains a bachelor's degree or not, I find that being more exposed to video games as a teenager leads to men to be less likely to obtain a bachelor's degree compared to similar women. So 1 standard deviation exposure increases the gender gap by 1.5 percentage points in favor of women. So that's a little harder to state because, as you know, women are more likely to get bachelor's degree in the US. And so it's an increase in the gender gap in the favor of women because it makes this gender gap basically larger. So this also has some important implications, and I tried to understand where this is coming from. So the sources of the effect that I identified comes from 3 different sources. So first, men who are more exposed to video games are more likely to get a technical degree. And this seems to make sense. So potentially some of these children are interested in computers, and then they don't need a bachelor's degree, for example, in order to get these jobs. So they are, if they are exposed to video games, then they are more likely to get an associate's degree, which is a 2-year degree in the US. So 1 standard deviation greater exposure leads to a 13% lower gender gap in the rate at which men get a technical degree. And it also, however, the effect also comes from these men being less likely to ever attend college. So this includes associate's and bachelor's degrees. I find that this is around half of the effect that I estimate. And they're also more likely to drop out. So to only do part of a degree and then never get any certification. I'm not able to explore whether these technical degrees are in computer science because the survey doesn't include field of study if it's not a bachelor's degree. But this, I guess my suspicion would be that it is, yes. Okay, and these are just those results as regressions and in detail that, as you can see, men more exposed to video games are more likely to get these associate's degrees. And here's the breakout on the probability of ever attending a university and of decrease in the probability that these men are getting a degree, even if they conditioning on the fact that they at least attend university at any point in time. In terms of robustness, so I conduct a lot of analyses. This was my job market paper in economics, so it's a long paper. I really vary my analysis in many ways to try to make sure that these results are convincing. So I vary the length of the cohorts, for instance, in which I group people. So I don't do it at the year level. I do it at the 4-year level, so that since estimating treatment periods at the 1-year level is it's a little bit too much, and so I vary the length of these cohorts, and my results are consistent. I just get slightly smaller effects if I use smaller cohorts, presumably because there's a shorter period of exposure. This is also the case with the age at which I measure people's video game exposure. So in my results that I showed you, I'm using ages 10 to 17, but the results are the same if I use ages 12 to 15, which is the age in which video game use is highest from what the literature currently says. I also am using the state level because that's the level at which I know where people were born. However, I try to also reproduce the analyses using metropolitan area information, using the current residence of respondents in the survey. And results are generally consistent. The issue here is that I am unable to separate the extent to which the effects are coming from adults who study computer science working in specific parts of the country. So that's why I prefer to use location of birth. And I also try to use different measures of sales for my instrumental variables. So sales in specific genres, for instance, average sales, total sales, and the results are also generally consistent. I normalize my instrumental variable by population instead of by area. The issue with this is that, a lot of it's hard to distinguish how much of the results are driven by large states versus small states. And I also vary the arcade data that I use. And one additional robustness is that I also explore the extent to which my results are driven just by exposure to computers. I find that the thing is, computer exposure is very correlated with video game exposure. However, my results, I'm able to capture a larger share of this effect. And also, once I break out the results by gender, I see that in fact exposure to computers doesn't have the same pattern on the gender gap in computer science, and in fact has the opposite direction of effects. Okay, yeah, this is just that table. And so all in all, the results show that video game exposure is associated with a larger gender gap in computer science and at the college level and in employment. One standard deviation increase in exposure leads to between 8 and 26% larger gender gap at the undergraduate level and 6 to 15% larger gender gap in computer science occupations. And since between the oldest and youngest individuals in my sample, we see over 50 percentage point increase in video game exposure, then the approximately 20 to 60% of the gender gap, increase in the gender gap in computer science bachelor's degrees could potentially be explained by this larger exposure. However, I also find that boys who are more exposed to video games are less likely to obtain a bachelor's degree at all. And so all in all, taking these results together, the findings are that there are potentially very long-lasting heterogeneous effects of video game exposure on boys' academic outcomes. And to conclude, identify an association between the spread of video games and gender segregation in computer-related fields. I use a novel instrument video game exposure to provide causal evidence of this link. And I also identify these complex effects on educational outcomes. And to the best of my knowledge, this is the first paper to find an effect on video game exposure on career choice. And since video games have become more and more popular, as I showed you before, men dedicate now over 2 hours per day on average to playing. Then I think that this paper could have really large policy implications that we should explore. So my results highlight the importance of non-academic activities during childhood on long-term outcomes and career choices, and hopefully raise the focus and attention given to differences in gender in these activities and how these could be important drivers of occupational segregation in the long term. And that's it. Thank you.
Perfect, Claudia. Yeah, you got applause. Yeah.